Great. So welcome once again. Welcome to everybody. This is an NITheCS SATACS course. NITheCS stands for National Institute of Theoretical and Computational Sciences. It's a new institute set up in South Africa. And SATACS stands for South African Theory and Computational School, which is a program under NITheCS for running lectures like these. We are going to begin from the beginning, unless all of you tell me that you already know quite well what a category is. Is there somebody in the audience who does not know what a category is? I hope there is, because then I can proceed with what I've prepared to tell you. So you want to maybe put it in a chat if you're such a person. If this is your first encounter with category theory, let me know in the chat. Okay, there we go. I see somebody raise their hand, so I suppose that is so. Well, yeah, thanks, Alexandre, for your comment. So every time I do this, I start it from a different angle. So you can also go back to previous lectures and see how possibly I started in a different way and a different year. Today, I'm going to start with something quite basic, which is not the usual starting point, because usually one assumes that it's so basic you don't even mention that. I'm going to start with the concept of an object in a category. In fact, we're going to start with the concept of an object, irrespective of where the object lies. So in category theory, when we talk about an object, we mean a certain entity where the information about the entity, the internal structure of the entity, is kind of hidden away from us. We're not focusing on the internal structure of the entity. We're focusing on this entity as something observed from outside, and then later on we will be interested how this entity interacts with other entities. So it's an entity where the internal structure of the entity is not revealed to the observer. Now you might ask, what could be an object? And the answer is, in fact, any mathematical structure could be an object. And it doesn't even have to be a mathematical structure. It can be something from the world around us. A good example of this analogy, or rather an analogy for explaining this concept would be a radio. Imagine you've got a radio. Well, we don't use radios anymore these days, but we've got a radio, and it has quite a complicated structure inside the radio, but we don't really observe that. What we observe is what we hear from the radio, and we can also interact with the radio by maybe putting the volume up and tuning the channel, right? So we kind of interact with the radio through its external structure. We basically, it's the interactions with the radio that we perceive more than what the radio is made out of. We never open up the radio and look inside it when we just listen to it. Something happens externally, but of course, the fact that the radio is able to transmit information and so on, it's because of its internal structure. It's just that we are not observing the internal structure. We're observing rather the effect of that on other things like our ears, for instance. What would be another good example of an object that would draw a similar analogy? Who would like to propose one? So one is a radio. What shall we put as example two? The internet. Um, the internet would be a bit challenging because we would have to be kind of observing it externally, so to say. So it's a bit difficult for me to imagine myself observing the internet externally because it's so big. In some sense, it surrounds me everywhere. Maybe a better example is what Brian is suggesting here: a human being. A human being is like a radio, isn't it? When we interact with a human being, we don't really look inside what's happening inside the human being. We don't really observe the internal structure of the human being. We kind of interact with it externally. Like now, when we're talking to each other, or when I'm talking to you, you hear my voice and my you can maybe see me also on the video, but you don't see the processes in my brain that lead to the words that I say and so on. So a human being is also a good example of an object. The next concept is that of what we call in category theory morphism between objects. The morphism between objects can be thought of as a process that goes on between these objects, but it has a direction. It's almost like some kind of one-directional information exchange. A morphism between objects, let's say between objects A and B, is a process that happens from A to B. And we draw this as an arrow. So if A and B are objects of mine, then a morphism will be drawn as an arrow that connects A and B, and it goes out from A and it goes into B. If this morphism is the name F, then we would say that A is the domain of F, and B is the codomain of F. Me now talking to you is an example of a morphism. So let's say I am object A, and let's say Alexandra is object B. I'm saying something, and he's hopefully listening to it. And so some information flow is taking place, right? So there's a certain process which is a direction. The process being of me talking to Alexander. And so that would be an example of a morphism between objects. So example one would be conversation between two people. But of course, it could be that not only A is saying something to B, but it could also be that B is saying something to A. So there is another process happening backwards. So in this case, we have two morphisms, one going from A to B, and the other going from B to A. And these are people, so maybe I should draw them as such. Now, it could also be that I talk to, so let's say this is Alice, Alice and Bob. Okay, maybe this one is Bob, and the other one is Alice. So Alice could say something to Bob today, but then tomorrow Alice could also say something to Bob, and that would be maybe a different morphism because we want to distinguish what has been said today and what has been said tomorrow. So we could maybe have G1 and G2, where possibly F is everything Bob told Alice, whereas G1 is everything Alice told Bob today, and G2 is everything Alice told Bob yesterday. Could you suggest another example of a morphism between objects? So this was our example one. I hope it's clear. If you have any questions, please do ask or suggest another example. Talking to oneself, that's interesting. That happens, right? That happens sometimes. But okay, well, we could maybe, I wouldn't want to call this a different example because it kind of fits nicely the previous example. We could maybe also have an arrow that goes from Bob to Bob. Let's call this H. And H is everything Bob is thinking. Perhaps that is good enough. It doesn't have to be necessarily saying out loud, because even if you think, you can hear yourself, unlike Alice, who wouldn't be able to hear what Bob is thinking, so he actually has to talk. It's an interesting example because in this case, the domain and the codomain are both the same object, right? Remember, the domain of F was the starting point of F, of this process F, and codomain was the ending point. But here, the start and the end are the same. In both cases, it's Bob. So Bob is both the domain and the codomain of this morphism H. But let's think of an example that is of different type, that has nothing to do with conversation. Entirely different type of example of a morphism. What would that be? Roads between towns, train systems. Yes, that's fantastic. So we could have train stations. So there could be one train station, and there could be another train station, and there could be a third train station, and this could be different cities. Maybe you can tell me which cities you're listening from, and I could put your cities here. So I'm in Stellenbosch at the moment. Okay, so I want to pronounce this correctly. Nanjing, is that correct? Maybe could you teach us how to pronounce that? Okay, fantastic. Thank you. And then we've got Bonn. So imagine we have train lines connecting these towns. So there could be one from Nanjing to Bonn, and there could be one from Bonn to Stellenbosch. Well, in real life, probably there are not really any such train lines because these cities are quite far from each other. But of course, there could also be several train lines. And some of these train lines could be carrying trains in one direction, but they could also be carrying in the other direction. So we could have various directions here as well. Let me put these arrowheads to indicate the directions. Maybe here, it's possible to go to Nanjing to Bonn, but it's not possible to go the other way around. But between Bonn and Stellenbosch, maybe there are possibilities of going back and forth. So these would be some of our morphisms. It is going to be a long ride. That's right. And somewhere in between Stellenbosch and Bonn, we can pass Nairobi, Brian. Okay, so I hope that the concept is clear, the concept of object and the concept of morphism. Now, the next concept for us is that of a graph. So let me number these concepts. So this was concept number 1, the concept of an object. And then we had concept number 2, that of a morphism. And now let's look at concept number 3, which will be a concept of a graph. The term graph is used in many different ways in mathematics, right? We have graphs at school when we plot the graph of a function. We have graphs in graph theory, where we have nodes connected by edges. And so we also have graphs in category theory, and they're almost the same as graphs in graph theory. It's a bit more subtle, though, in the sense that we have nodes there as well. These will be our objects. And the edges are directed because we want our morphisms to have direction, but also you can have multiple edges between any two given nodes. Like, for instance, in this Alice and Bob example, we think of Bob and Alice as nodes of a graph. Then we have one directed edge going from one way to the other one, and then we have two of them going backwards. So a graph is a class of objects and a class of morphisms between these objects. Now, why would we want to consider a concept like that? Why would we want to restrict to only certain objects? Because that's what's going to happen, right? If we only take objects in a certain class, it means that I'm not considering all sorts of objects that exist anywhere in the world. I'm only considering certain type of objects. Like even these examples, there was some kind of suggestions for what the graph should be. In example 1, it seemed like we're considering objects to be only human beings. So our class of objects is just human beings. These are the only objects we are interested in as far as example 1 is concerned. Or somebody else could say, maybe the way we drew example 1, we actually had only 2 human beings, specifically Alice and Bob, and there was nobody else there. And then also we identified only certain morphisms. In this case, it was 4 of them. So we restricted all possibilities to fewer possibilities. In the second example, it seemed like we wanted to consider as objects just the train stations and the morphisms just being the train lines. And of course, in general, when you want to do mathematics, that's what you want to do. You want some kind of a restriction so that you can focus on some aspect of whatever you're studying. Otherwise, if you study everything at once without any restriction, it's too complicated, right? Basically, that's what a graph is. It identifies for us some fragment of the universe which has some specific objects in it. I'm only interested in those objects. I'm not interested in others. In that specific graph, I'm only interested in those objects. And then also it identifies some specific morphisms that I would be interested in. And so the picture would be that a single graph, which I can think of it. Hi there, What a fella. You want to ask something, or should I just um maybe?
Please.
Okay, great. Yeah, thanks. No. Okay, so a single graph is what? It's an object itself, right? But now its internal structure is given by some objects and some morphisms between them. And these have to be named in advance. We should not have a dispute as to which objects and which morphisms go in a specific graph. The single graph is a pair. We can think of it as a pair consisting of O and consisting of M. So of a class O of objects and a class M of morphisms. And we assume here that every morphism remembers what its source is and what its target is. In other words, what its domain is and what its codomain is. Here's a question on the chat. Does this mean the objects and their morphisms determine what the graph is? Absolutely. The graph is completely determined by what are its objects and what are its morphisms. Keeping in mind that every morphism itself determines what is its domain and what is its codomain. Okay. So once we focus on some fragment of the universe that's given by certain kinds of objects that we've included in our graph and certain kinds of morphisms, we can now study the structure of this fragment of the universe. And the hope is that by studying this structure, we get some information about the world. Now, in such a study, we really want to think of these morphisms as processes going on between the objects. And one fundamental question that arises when you're studying the structure of processes is, when do two processes give the same result? So let me elaborate on that on an example. So let's consider a specific example of a graph. This is our example one of the graph, of a graph. In this example, let us take our class of objects to consist of a single object. There's only one object in our graph, okay? Class of objects consists of a single object. And that single object is the set of natural numbers. N. Now the morphisms are functions. And of course, in this case, there will be functions from the set of natural numbers n to the set of natural numbers n. And here is some examples of such functions. So let's take n. Let's take the function from n to n that basically adds 1 to a number. So the successor function. You take a number and you add 1 to it. You can think of this as a process that transforms every number to its increment by 1. 2 will be transformed to 3, 4 will be transformed to 5, and so on. So that's one morphism that now runs from n to n. I would prefer to draw it this way rather than draw it as a loop, although it is actually a morphism that's a loop because the domain and the codomain in this case are the same. Let's take another one that multiplies a number by 2. 4 will get transformed to 8, 5 will get transformed to 10, and so on. Now let's take a third one that will square the number, okay? So we get a sequence of morphisms in our graph, and there is a certain overall effect that this sequence of morphisms has. What do I mean by that? So if I pick a number and let us display the process of picking a number itself as a process. How do I display the process of picking a number as a process when all my objects are just natural numbers? I'm not allowed to take any other object, right? I can still think of picking a number, a specific number, as a process that goes from end to end. Who would like to tell me how can I represent picking one number as a process, as a morphism from end to end? If we, so that answer is wrong. Somebody said, just write n, identity. So that would be something that transforms every number to itself. But that doesn't pick a single number. I want to pick out a single number. From the set of all numbers, I want to choose one number. I want to make one number special. So I want this entire process to just generate one number as a result of it. I don't want to assign a number to itself, because then that will not be selecting any specific number. And specifically, I want to pick number 1. How can I represent the process of picking a number as a process from end to end? There we go. We got some nice suggestion there. We should take the constant number, the constant function, right? Let every number transform to 1. That's a fantastic suggestion. Thank you there, August. So we will write it as 1. So it's a function that maps everything to 1. It's a constant function 1. Okay, so we can now trace the effect of this entire path of processes. We begin here, right? We begin here. And then an arbitrary number we pick here, let's pick n, will get transformed to 1. Then 1 will get transformed to 2 by the next process. The further on, 2 will get transformed to 4, and further on, 4 will get transformed to 16, right? We could have another chain of morphisms. For instance, we could still be picking the number 1. Then we could be squaring it. Then we could be squaring it again. No, that wouldn't do what I wanted to do. So let me instead not pick here number 1, but rather pick number 2. We can square it, then square it again. Sorry, I should write 2 here. Square it again, and then I want to display this as going straight there. So what will happen to what kind of process will be this combination of these processes? So I go from end to end by picking 2, so everything goes to 2 here, and then it gets mapped to 4, and then of course it gets mapped to 16, right? So what do we observe? We have 2 different paths of processes, but the overall effect, even though they're different paths of processes, you see this is this path is very different from this one. Well, how is it different? Well, this one has 4 processes involved, right? There are 4 morphisms involved there. Here we have 3 of them. Moreover, there are some morphisms involved there, like 2 of them, which are not even involved here. So they're entirely different paths of morphisms, but their overall effect is the same. If we go back to our train example, it's a bit like saying that I would need one more morphism here, I think, to illustrate what I want to say, or maybe not. So I could go from Stellenbosch to Nanjing, and then I could travel from Nanjing to Bonn, right? I'll be taking train from Stellenbosch to Nanjing, and then from Nanjing to Bonn. So I'll be going along this path of morphisms. The overall effect of that will be the same as taking direct train to Bonn. Of course, I will not see the beautiful city of Nanjing along the way, but at this stage, I'm not interested in the intermediate story. I'm interested in the final outcome. And in terms of the final outcome, in both cases, I will be getting to Bonn. So that's another example where you can have 2 paths of processes yielding the same overall effect. Do you want to ask any questions on this idea? So we have 2 paths of morphisms in this graph, giving the same overall outcome. Here's a question on the chat. Does the beginning always get us to the same end because of what the process is and what the objects are? Well, it is very specific to these 2 paths that the outcomes were the same. I could have had different paths where the outcomes would not be the same, right? For example, imagine if instead of 2 here, I had started with a different morphism, 3. Then I would have gotten, along the way, I would have gotten to 81, right? So this would have been 3 maps to, so every number n maps to 3, and 3 maps to 9, and 9 maps to 81. So now suddenly I have a different path. I slightly changed my path, and suddenly I have a different path that no longer gives me the same outcome. So we can't in advance tell whether 2 paths will give me the same outcome or not. Actually, this is in some sense the most fundamental question we want to ask about our graph. When are 2 paths of morphisms, when are they yielding the same outcome? Just to give you another example of this, so imagine you want to build something, right? And you want to maybe build a beautiful tower. And so you have to do something. You have to instruct the engineers to do something. They will have to instruct the workers to do something. There's not lots going on there. Not just the engineers and workers will have to get a permission from the town to put a tower in the town. So it's a very complex structure of processes. And then at the end of the day, the overall outcome of that very complex structure will be the tower standing in the town. But now in the beginning, you had an idea of how this tower should look like and where it should be positioned. So you want to compare that outcome, that overall outcome, to what you had in mind. And you want to make sure that the overall outcome will be what you had in mind. You don't want to go through this process and then eventually build a bridge instead of a tower, right? It has to be a tower. So it is important to know what to do which processes to take at each stage to get to the outcome you want to. So figuring out when does a sequence of processes lead you to a certain outcome is, in a sense, the most fundamental question about studying a graph. So there's a question there in the chat about in this example of a graph. So in this example of a graph, we had only one object, and that object was the set of natural numbers. So if I draw my graph, so if this is my graph, there I'm considering, and I zoom inside its internal structure, what I will see there is a single object and lots of different morphisms that are looping on this object. These will be all possible ways of mapping things, all possible functions from the set of natural numbers to the set of natural numbers. That's how the graph that I'm considering example 1 here, that's how that graph will look like. I hope that answers the question that you asked there, Brian. But what I was actually doing with this example is to lead you to the next concept, and this is the concept of a path of morphisms. This is our, let me see the numbering here. This is our 4th concept. A path of morphisms is a sequence. Okay, well, first of all, I should say that we are inside a specific graph. So let's fix a graph. So a path of morphisms in G. Let G be a graph. So we are now assuming we are working in a specific graph. Then a path of morphisms in that graph is a sequence F1, F2, F3, and so on. It can go up to Fn, where n can be arbitrary number, is a sequence of morphisms such that codomain of Fi, remember this is the target, this is where the arrow goes into. Codomain of Fi is always equal to the domain of Fi plus 1. So that happens for all I in the set 1 up to n minus 1. Visually, this will look like this. I've got my F1, I've got my domain of F1 object, then I've got my codomain of F1, and that must be the same as the domain of F2, and so on. This is F2. And it will go on like that. So let me draw a couple of more. So F2 will go to wherever F3 leaves, and it will continue like that, eventually coming to the last morphism Fn. And so here we'll have the codomain of Fn. Right? Now, if I call this object X and I call this object Y, so when X is the domain of F1 and Y is the codomain of the last morphism, we say that the path is from X to Y. Okay. Going back to the previous example, we had example here of 2 paths. This was one path. Here one was F1, n plus 1 function was F2, 2n function was F3, and so on. And we also had another path, this one, where 2 was F1, n squared was F2, n squared was also F3. So it was a path where some of the morphisms repeat, and that's fine. Morphisms can repeat. I might want to, in my travels around the world, I might want to go from Stellenbosch to Bonn several times. In this case, both of these paths were from this object, the unique object in our graph, the set of natural numbers, to the set of natural numbers. Let's see now some of the questions on the chat. So anything can go into it with certain processes used, but we need to know what will get us to building that tower, regardless of what it looks like or the size, because our result is what we call a tower. Yeah, so we actually we want a certain looks from the tower maybe also. So there are certain criteria we want the tower to satisfy. We want it to be a certain height, to have a certain position, and so on. And then we're trying to figure out what processes, what paths of processes we should take that will get us to that result. So I think we're on the same page there. And then there's another remark. I see why people say category theory is used in scaling laws of AI. Well, I'm not sure I know what scaling laws of AI are, but maybe from the remark you make, maybe I can take a guess, and then I would agree. Okay. So now this is the concept of a path of morphisms, and the reason why we want to consider that concept is to be able to say when two paths of processes have the same effect or not. So we actually need another concept, and that will be the concept of equivalence of paths. Two paths, let's say f, written out as f1 up to fn, and g, written out as g1 up to gm. So g, the name g stands for the entire sequence, and its terms, the individual morphisms, we write g1, g2, g3, and so on, and the same for f. So two paths, f and g, but they have to be now from the same object x, from an object x, to an object x, sorry, object y, to an object y, are said to be equivalent when they yield the same outcome. Going back here, we observed that this path and this one, we observed that they did give us the same outcome. In both cases, we were mapping all the numbers into number 16. So they both give the same end result. And that's exactly what we will call equivalence. So what we observed previously was that this path of morphisms is equivalent to this path of morphisms. Okay. Let's look at another example of equivalence. I'm gonna take this off. So example one of equivalence. Let's think of an example from real life. Let's consider a graph where objects will be human beings. And let's try to build two paths that will be equivalent. So let's begin with some person here. This is maybe Bob, once again. And here we've got Alice. But now let's introduce some more characters into the story. There's somebody maybe called Mark. And then there is somebody called Jane. Now, Bob wants to transmit some message to Alice, but Bob and Alice are maybe far from each other. So Bob has a friend, Mark, that he can say something to Mark that Mark can transfer to Alice. And so maybe Bob says to Mark that he's fond of Alice. Okay. Now Mark is also fond of Alice, and as such, he knows that Alice could have some affection towards Bob, so he actually doesn't want Alice to know that Bob is fond of Alice. So, so Mark tells Alice something completely different. Mark tells Alice that Bob doesn't like Alice. Now, Jane here. Jane is also interested in to know. Jane is interested to know what Bob thinks about Alice. Jane is a good friend of Bob, and Bob is kind of embarrassed in front of Jane that he likes Alice for whatever reason. So he actually tells Alice that he tells Jane that he actually doesn't like Alice because he was embarrassed to confess that he likes her. But it turns out that Jane is actually a good friend of Alice, and Jane is very honest to Alice. She always tells Alice whatever she hears. So Jane conveys this message of Bob to Alice that he doesn't like Alice. Now, do you think that this path would be equivalent to that path? Okay, so I agree with you. I agree with you, Alexandra. So they will be equivalent because in both cases, the total outcome of this whole story is that Alice finds out that Bob doesn't like Alice. But notice that the paths were very different, right? So the process that led to this outcome were very different from each other. What happened here is extremely different from what happened there. Okay, so as I said before, this concept of equivalence is a fundamental concept. And as such, perhaps we want to define it precisely. Well, it seems like we already defined it here. We said that two paths are equivalent when they yield the same outcome. But is that a definition? Before the process finished, how will I know that they yield the same outcome? I might not know, right? So what it means to yield the same outcome might be actually the unknown we want to solve for. So it is not a satisfying definition from that point of view. But we still want to know what we're talking about mathematically when we talk about equivalence of paths. And in cases like this, when we want to introduce a mathematical concept that for which we are not able to formulate a precise mathematical definition, because indeed, I mean, in each different environments, in different graphs, yielding two paths of processes yielding the same outcome might be for different reasons. So there might be different rules that govern those. So in cases like this, where either I cannot give a mathematical definition, or the definition actually depends on the context, right? In cases like this, we use an axiomatic approach. we cannot define what is equivalence of paths, but we can say what are the fundamental principles it must obey. Let's try to uncover what these rules should be. So what we want to do next is to develop an axiomatic approach to equivalence of paths. Okay. We want to define equivalence of paths in an axiomatic way. Okay, so the first thing we can say is that an equivalence is a binary relation, right? It relates paths with each other. It's a binary relation that relates paths having the same source and the same target. So as a structure, it just consists of pairs of paths. So one path, another path, they form an equivalent pair if intuitively if they yield the same outcome. But now we want to formulate the laws that this idea of yielding the same outcome will satisfy. What should be the laws of equivalence of paths? I hope I didn't lose you at this point. If anyone is not sure what we're doing, please do let me know in the chat. I can go back to the motivation. But otherwise, you might want to suggest what do you think should be one of the laws of equivalence of paths. Right, so there's a suggestion there, same domain and codomain and preimage and image. Sure, that's what was kind of implied with what we said there, but maybe we should formulate it more explicitly. So let's say that when two paths, F1 up to Fn and G1 up to Gm are equivalent, let me rather say if, then the domain of F1 must match with the domain of G1, and the codomain of Fn must match with the codomain of Gm, sorry. So it kind of tells us that we only want to consider this idea of equivalence of paths when they connect the same pair of objects. It doesn't make sense to talk about equivalence of two things if these two processes do not go out from the same object, do not end up in the same object. And they certainly can't be equivalent anymore because of this distinction of their source or their target. So this seems to be a very natural axiom. There's another suggestion there, composition works. Well, Alexander, that's exactly what we want to define here. We want to define what does it mean that it works. So we are trying to identify axioms that will capture that. You referred to the term composition. We haven't introduced that term before. If what you have in mind there is what you know is a composition in a category, well, we're trying to build to that concept. We will see later on that the concept of composition will emerge from this idea of equivalence. But first, we want to formulate a bit more properties or laws of equivalence. In general, when you have a law of equivalence, there is even something called equivalence relation in mathematics, right? You want it to be reflexive, you want it to be symmetric, you want it to be transitive. So maybe we should require these as well. Yeah. Equivalence must be an equivalence relation. So what does that mean? So if I have one path, F1, Fn, and if that is so if I've got one path and that is equivalent to another path, right? And that is further equivalent to a third one, then probably I want to be able to conclude from this that the first one, the first path, is equivalent to the last one, right? Would you agree that this is a natural requirement? So let's visualize this. Imagine I have a process, a sequence of processes that yields the same result as the second one. And that second process again yields the same result as a third one. So this gives me the same result, exactly the same result as this process, but I also know that this process gives me exactly the same result as this process. Can I then not conclude that the first one gives me the same result as the last one? Surely that should be a natural thing to require. So in this example, F1, F2, F3 are as follows. Then we've got G1, G2, and G3 here. And here we have H1 and H2. We would call this transitivity of equivalence, right? Because that's how it's called for general equivalence relations. So this is the law of transitivity. Then we have law of symmetry, where if one path is equivalent to another one, then we also want the backwards relation. And we can also say that the other one is equivalent to the first one. And this is called the law of symmetry. And I hope this is also quite natural, because when two things yield the same result, then it doesn't matter in which order I mentioned that they yield the same result, right? There is also law of reflexivity, which says that any path, every path is equivalent to itself. This is our law of reflexivity. So these are the three usual laws for all kinds of equivalence relations out there. And I'm kind of assuming that everybody here already knows what an equivalence relation is. If you don't, then you see the definition is here. But is this enough? That's the question. Do we want to say more, or do we want to stop here? Do we want this to be an exhaustive information about our general notion of equivalence? So the question we're asking now is, are the laws, namely reflexivity, symmetry, and transitivity, enough for defining the concept of equivalence of paths? So there is a comment, isn't that sufficient information to give us equivalence? Yeah, if it was, if instead of morphisms we had some set of abstract entities, right, which are not related to each other in any way, then these three laws, reflexivity, symmetry, and transitivity, is the best we can do. But in our case, we are defining equivalence of paths, and paths have structure, right? They have starting point, they have ending point, they also have all these intermediate points. And surely when you have a bit more structure on your set, you want to say a bit more what it means for things to be equivalent. Like, just to give you an example, let's take integers, right? And let's consider the notion of equivalence in the case of integers. There's a beautiful notion of equivalence in the case of integers, which is the notion of congruence, that two integers are the same modulo certain integer. The congruence relations on integers, are they just reflexive, symmetric, and transitive, or are they more than that? And of course, the answer is that they're more than that. Just reflexive symmetry and transitivity doesn't give you a good enough notion. This notion of equivalence will not be interacting nicely with the structure of integers. The same can be said about groups in general, or other structures. But now let's not talk about other structures. Let's focus on our intuition for what we're trying to capture here. We're trying to capture the idea of two sequences of processes yielding the same result. And we want to be clever in describing the laws of the sameness, the laws that the sameness should satisfy. So there is one law that we still need. Well, if we are clever, we can formulate it as a single law, and then we'll be good to go. And I would like to suggest you to maybe take your guess. What do you think that law should be? Try to think of something that relates to the existing structure of our graph, to the fact that we actually have these morphisms that run through between the objects. Maybe I'm going to prepare a little hint for you that will be based on this example. Let's say I started my travels not from Stellenbosch, but I started my travels from Tbilisi. And let's say I want to complete my travels not in Bonn, but in Tallinn. I hope I got the spelling right there. No, sorry, it should be double L, right? Is it double L and double N? Let me quickly confirm that. Yeah, I think I got it right. And remember, previously we remarked that the overall effect of taking this path, going from Stellenbosch to Nanjing and then to Bonn, is the same as going directly from Stellenbosch to Bonn. And I already know that. From this, will I be able to conclude that taking this route is the same as taking this route? So this is a simple example, but actually something very complicated might be happening here, right? And so it might be a big effort to actually confirm that this does give the same result. After all, I have to take these training lines and check that I will really arrive in both cases. So if I have a longer path, I wouldn't want to check it again, especially if it takes a lot of effort to do that. So knowing that something happens locally, some equivalence happens locally, it is useful if from that I can infer that equivalence also takes place globally. And that is the hint to the axiom that we're missing. The one other law that we want to formulate that equivalence should satisfy. Okay, so what is that law? Let me first draw the picture. So let's say we've got objects W, X, Y, and Z. And we have a path here, a certain path. Let's call this path F. So F is now the name for the entire path. And we have another path here. Let's call it path G. Okay. And we already know that the paths F and G are equivalent. Then we should be able to infer the following. So if I have further paths here connecting W and X, and I have a path connecting Y and Z, then I should be able to infer that the bigger path, this one, is the same as this one. Would you agree on this as being one of the fundamental principles of equivalence? So when I said the same, I meant equivalent, right? So let me write this out while you think whether you agree or not. Given two paths, F1 up to, let's say, I'm going to call the whole thing now F instead of splitting it into F, G, H, and I. F1 up to, let's say, FR, and then it goes all the way up to Fs, and then it goes further on up to Fn. So we have that, and we have another one which has the starting point the same. So if it goes from F1 to Fr minus 1, let me actually call that Fr minus 1. And then instead of Fr, it has F prime R. And it goes to F prime S. And after that, it continues exactly the same way as the other one did. So Fs plus 1, Fn. So if we've given two such paths, where the path Fr to Fs is equivalent to the path Fr prime to Fs prime, then those two paths will also be equivalent. Then this must be equivalent to this. So is this something that you would agree with me on, or do you want to dispute it, or maybe question it, or maybe ask me to re-explain some aspect of it? Please give me some feedback so that I know. Thanks, August. I will call it law of congruence. If you'd like to ask a question just by unmuting yourself, go ahead, please do that. At any point, you can always interrupt me and ask your question. But it seems like we all agree. Maybe I want a few more agreements before I know that we all do agree. And Okay, fantastic. It's similar to saying the relation is compatible. I think you wanted to say compatible. Yeah. Yeah, sorry, you do say compatible. I read it as comparable for some reason. It's a similar concept to the concept of being compatible indeed. And in fact, one can even phrase it to be exactly the same concept if one introduces a bit more terminology. So these are the fundamental laws of equivalence of paths in a graph. So what are they? There are four of them. There's law of reflexivity, there is law of symmetry, there is law of transitivity, and then there is law of congruence. We might want to have a fifth one. And the fifth one, we might want to be the following. If two paths that have the same length of 1, so if path F just consisting of one morphism is equivalent to the path G, then we want these F and G to be equal to each other. So why would we want that? So imagine now these F and G are morphisms from A to B, right? So they are now single processes, right? There's no longer a path of process. It's just a single process. And this single process F and the single process G are giving the same outcome. They might be different processes, but they're giving the same outcome. We then might not want to distinguish them. To convince you that this axiom might be reasonable, because in real life it's highly unreasonable, right? Because I can get the same outcome in different ways, and so the processes are different, but the outcome is the same. We want to distinguish these two things. But when we do mathematics with these, we often start to disregard. Not always. Sometimes we still want to distinguish them. There are many examples where we do want to distinguish them. I'll tell you another one just now after this, where we want to distinguish them. But in many cases, we don't want to distinguish them. And here's an example where we don't want to distinguish them. So consider an example where we have two processes from, let's say, real numbers to real numbers. So again, there will be functions. Okay. So one is the function given by x squared. And the other one is a function given by taking the absolute value of x and squaring that. When we write this down as functions, as expressions, so let me write this down. This is expression x squared, right? And this is expression absolute value of x squared. These expressions look different from each other. And indeed, in fact, one of them does kind of decompose as a path of processes, right? It's first taking the absolute value. This really kind of stands for first taking the absolute value and then taking the square, right? But we're not thinking of this now as a path of process. We are thinking of it as a single process of its own, okay? So there is something different between these processes, right? The way that the number is manufactured in each case is different. In the first case, we pick a number, we square it. In the second case, we pick a number, first we take its absolute value, then square it. But when we talk about these two functions, the function x squared and the function absolute value of x squared, we will say that they're the same function, not equivalent functions. We will actually say that they're the same functions. Why we say that? Because we don't want to distinguish functions between each other if they yield the same outcome. And in addition, their domains and codomains being the same, right? So this example does satisfy our fifth axiom, our fifth law. If I've got two paths having each of them just having length 1, so in other words, each of them having just a single morphism in it, and they're equivalent, then they must be equal. So Another example where we're not going to have equality, so that this fifth law will fail, is the following. Consider some topological space, and if you don't know what a topological space is, that's fine. You can just consider the real world around you. Yeah, so thanks for that comment, David. So indeed, now we're going to give an example where we do want to see them as different, okay? Consider some point in space in your topological or the real world space around you. Consider 2 points there, one point A and the other is point B. And these points are now going to be objects of our graph, okay? And also any other object, any other point in the space would have been an object. Now a path, a morphism from one point to another one is a trajectory of traveling from that point to the other point. So we can imagine a particle that doesn't have any width, breadth, or any dimensions, just a infinitesimally small point, travels in this space. So we get some kind of trajectory of travel, right? And there could, of course, be many ways of traveling. Now, the outcome in both cases is that from A we arrive to B, but we might be interested indeed to consider the path that we need to take. I mean, this actual physical trajectory we want to take. But then let's define these two to be equivalent to each other if there is a continuous way to transform one to the other. So this is notion of homotopy. Many of you might be familiar with it. So we will say that F is equivalent to G when there is a continuous way of transforming F to G. And one way you can express that is to say that you've got a continuous function from 0, 1 interval times 0, 1 interval into your space S, where F was initially itself given as a function from 0, 1 interval to S, with F of 0 being the point A and F of 1 being the point B. Okay, and so you can think of this 0, 1 interval as a time interval. So initial time is 0, and the final time is 1. That's when the particle has arrived at point B. And then G is another such function, and let's say they both take the same time to go from A to B, and we don't have to rescale this. And so G of 0 will be A, and G of 1 will be B here as well. And now we could say that we could formalize this idea of continuously transforming. So what I mean by continuously transforming on the picture is that I could eventually deform this trajectory into the other one. So by infinitely many steps, and at no point I will make a break into my process of deformation, right? And so the way we can formalize this, and I'm sure many of you already know this, is to say that we have a continuous function h, which so what is the job of this continuous function? So this is basically our rectangle, right? It's a unit rectangle, and so we want to map all of these points on the rectangle. We want to map them to A, so they all get mapped to A. All of these ones, they map to B. So I'm just going to indicate it by labeling these with A and B. So all of these map to A, all of these map to B. This I want to map to where F maps them to. So I'm going to label that with F. So that maps to F. And that maps the same way as F. This maps the same way as G. And then I have all these intermediate lines that I was trying to draw there with a dashed line. I'll have these being the mappings of these intermediate steps. And I want this whole, now you can imagine this is a mapping of a square into some deformed shape. And I want that mapping to be continuous. And that mapping being continuous is a way of formalizing that it's possible to continuously deform this path, or rather this trajectory into this one. And so formally, I would require that H is continuous. I'm not writing that down. I'm assuming that also. I assume the same thing for F and G. I wanted them to be continuous. And then I also want to kind of formalize this picture, which would be saying that H of the pair 1x is the same as F of x. H of the pair 0x is the same as G of, is it the other way around? Doesn't matter. Yeah, no, it's this way around. G of x, and at the same time, I also want to say that H of y0 is always A, and H of y1 is always B. So this is a notion of homotopy of, so in topology, we call these things paths. We call these things paths. Obviously, they can be broken up, down into pieces like before. I could consider intermediate objects, and then I could have like this morphism, that morphism, they all being composed with each other in a path. So in topology, we say that this path is homotopic to this one when such a continuous thing can be found. And then we can write that, so we could say that F is equivalent to G, and we could put an index H to indicate this homotopy concept. So H itself is called homotopy. And of course, this is reflexive, symmetric, and one can also check it's transitive. And it's quite fun to check that. So if you haven't encountered this concept before, you might want to check why is this notion of equivalence, why does it satisfy the three axioms, reflexivity, symmetry, and transitivity? It also satisfies the fourth one, the law of congruence, because imagine I have something else here and something else here, right? If I know that this can be continuously deformed into that, then the whole thing, I will be able to continuously deform to this whole thing just by keeping these ends the way they are. They're still, because I don't need to change them because they're the same in both cases. And I'll continuously just deform this into the other one, like what I'm given that I can do. So the law of congruence holds, but this fifth law that we formulated, that one doesn't hold. Why? Because you see here, this is one trajectory. This is the other one. They are different from each other, but still they're equivalent. The fifth law tells me that if they're equivalent, then they must be the same. Just like here, if the function, two functions give the same result, they must be the same function. But there are examples where we don't want that. We don't want that fifth law to hold. Any questions so far? Is this are these ideas understandable? Did I do a good job in explaining them? You want to maybe clarify some points? Okay, fantastic. Okay, so oh, there's a good question, August. Is there any other name for the fifth law? Now I must make a confession to you, August, and everybody else. I have never seen anyone define a category, and that's what we're going to do in just a moment, in the way that I'm doing it here. So this is basically something that I prepared just for our lecture. So it's fresh new also for me, brand new also for me. And so I had to invent the names of these laws along the way. And the first three is not a big invention because they're familiar laws. The fourth one is also familiar. I took the term congruence from other contexts where this thing is called congruence. The fifth one doesn't ring a bell, but it has a name in other situations. So we'll have to come up with one, I guess. Would anybody like to suggest what we should call the fifth law? Let's have a little competition. Who can come up with the best name for the fifth law? And then we'll use that one. Isomorphism. Isomorphism is not the same as equality. Here we're doing something very strict. We're saying that equivalence must, of two paths of length, one, must reduce to equality. Congruequal. That's an interesting one. Congruequal. Wait a moment. Why don't we just call it law of equality? Because the outcome here is that they must be equal. So, so I'm going to call it law of equality until somebody can suggest a better name. Right. Now we're kind of ready to define what a category is, but our definition will be equivalent to the standard definition, but it will not be exactly the same. So we're kind of taking a path to the concept of a category that's a bit non-standard, but I think it's very intuitive because we've been able to motivate this from our understanding of processes, and that's actually a very important example. In some sense, all examples of categories are about processes in one way or another. So here is the definition. A category is a graph equipped with a relation of equivalence of paths that satisfies the laws of reflexivity, symmetry, transitivity, congruence, and equality. And I now realize that I might have forgotten one more law. There is one more law that I forgot about. I'm sorry about that. And the reason why I forgot about this is because we didn't pay attention to a special case of paths, which are called the empty paths. So I want to add one more condition to this, which I'm going to explain what it is right now. So we've got a reflexivity, symmetry, transitivity, congruence, equality, and one more law. And we're going to call this law identity. And it is the following. When we talked about paths, when we defined paths, we defined paths as a sequence of morphisms, right? And then after that, we said that we're interested to talk about paths that have some starting point and that have some ending point, right? So some object X and object Y. So if I have a path of morphisms, let's say F1, F2, F3, F4, and F5, it felt like we are always able to identify this object because it's the domain of F1, and that object because it's the codomain of the last morphism, F5. But I'm going to come back, Fosco, to your comment. We're going to definitely come back to that. But there's a problem. If my path has no morphisms in it, right? If it's an empty path, then I won't be able to pinpoint X and pinpoint Y, because X was supposed to be domain of F1, but if there is no F1, then what is X, right? So the correct concept, and we do want to consider empty paths. Why? Let's say, let me go back to this example. When we're traveling from one town to another by train, you should definitely take a rest. There will be points when you want to just rest. Don't go from that town. Just stay in the town for a moment. So if I'm staying in Stellenbosch and I'm not going anywhere, I want to be able to express that also as a morphism, basically as a process of doing nothing. And so that process of doing nothing is captured by the idea of empty path. But if I do nothing in Stellenbosch and if I do nothing in Tbilisi, even though I'm doing nothing, my state is still different, because in one case I'm in Stellenbosch, in the other case I'm in Tbilisi. They can't be the same thing, right? So the more correct definition of a path would be to start with two objects, X and Y, and then define a path to be something that connects them. So here is a better definition of a path. Given two objects, X and Y, in a graph, a path from X to Y is a sequence of morphisms. So from F1 to Fn of morphisms, where if n is bigger or equal to 1, then domain of F1 must equal X and codomain of Fn must equal Y. But the case when n is 0 gives me an empty sequence. So this is a sequence of morphisms from F1 to Fn. When n is 0, it means we have no morphisms, okay? So it's just empty sequence. You can think of it as an empty set. When I have an empty sequence, it is still a path from X to Y, except that in that case, because it's empty, we're not moving anywhere. So X and Y then must be equal to each other. So where if n is bigger or equal to 1, then this must happen. But if n is equal to 0, then X must equal to Y. Okay, so we have two cases of paths. Ones are non-empty paths where we actually have some morphisms in them. The others are empty paths, but in that case, the starting object and the ending object must be the same object. And then we can add the, with this notion, we can now introduce the identity law. Maybe I'll go to the side here. The identity law of equivalence states that for every object X, there exists a morphism We have a special notation for this morphism, but at this point we don't know if it will be exactly one or many. So we are not going to use that special notation for now. There exists some morphism E that will be from X to X, such that the path with E in it as the single thing is equivalent to the empty path of the object X. So if I write it with maybe a subscript X, and in general, the notation I can use for paths is I could say when I have a path, let's say, let me go back to this definition. When I have a path from object X to object Y, I could maybe say, I could maybe put X at the bottom here and Y at the top. And then here, I could think of this as a path from X to X, because it is. And then the other one is the empty path from X to X. So this is the fifth law. So it basically tells us that the process of doing nothing should also be inside our graph. Remember, our graph was, we selected some processes, right, between objects. We didn't select all of them because we didn't want to get a chaos. We wanted to select those we want to focus on. But now this law tells us that among those processes we selected, we must have selected one of them that represents doing nothing. In other words, that represents taking empty path of processes. Coming to a question of David there, does it mean that the domain of a morphism is non-empty? It doesn't mean that. The domain of a morphism could still be empty. Think of empty set as the domain of a function, an empty function that maps empty set into another set, X, let's say. You'll get their morphism that oh, but maybe what you were asking is no, sorry, yeah, okay. So if you're asking about morphisms in a graph, then we can have those objects in my graph being actually the empty set, and morphisms being maybe functions from empty set to some other set. Now, a question that Foska was asking, why the fact that the identification between paths reduces to strict equality on paths of length 1 doesn't imply that it reduces to equality on all paths by induction? I'm not sure I understand the question. I would appreciate, please, a bit of clarification, either by turning the microphone or expanding.
Yeah, I can try.
Yeah.
One of the rules is that if you have identification between two lists of morphisms in a path, then you can join something and something else on the left and on the right, and you keep this an identification. So if you start with the fact that the list that contains only F is equivalent to the one containing only G, implies that this F is equal to the G, like you can remove brackets from the list. Why doesn't this imply that I can deduce that F prime in relation to G prime means that F prime is equal to G prime as a pair, as a like strictly equal? Where is the subtlety in this?
That's a very good question. That's a very good question. I'm going to visualize this, and then the answer will emerge from the picture. So, so what we want to thank you so much for that. So what we want to do is to take this picture and look at this picture in a special case where F and G are only length 1, right? So let's do that. So we have F, and we are told that it's equivalent to G. And we're also told, but when we have this axiom of equality, that means that F and G must be equal. But now you're saying that we also have this law of congruence, which would allow us to say, let's say the path I, F, H, sorry, I should actually write the other one. way around, right? HFI, that path must be equivalent to the path HGI, right? But now we know that F and G are actually the same morphism because by the law of identity they must be the same. So we can rewrite this as HFI being equivalent to HFI. However, here we don't get anything new because we already knew that by reflexivity, by the law of reflexivity, these two paths would be equivalent. So so if I answered your question, that's great. If I didn't, you might want to re-ask it on this picture.
Well, I think I understand what is the point, but I believe I am half confused by this idea that somehow strict equality of lists of elements in a very general sense is defined so that each component in the ordered tuple is equal. And this is strict equality for lists. This is how
No. We are not. Maybe the confusion here is about the direction of implication. We're not saying that. So I'm not saying that if I have two lists, they will be equivalent only when they're term-wise equal. I'm not saying that. I'm saying that if I have two lists of length 1 and they're equivalent, then they must be equal.
Okay.
But if I have other lists and they're equivalent, then they don't have to be equal. So
the axioms that you gave are not enough to deduce that two lists of morphisms are equivalent if and only if each component is equivalent to each other. So that's the point. Okay, that's what was confusing me, and I think probably I hope someone else, or I would feel very dumb.
No, that's a valid confusion. I think it was quite a valid confusion. And let me also mention that we actually already have a counterexample for that because we got convinced that for functions between sets, law of equality makes sense, that it actually holds because we only distinguish functions when they have different effects. If they have the same effect, they're the same function.
Yeah.
And yet we had two different paths of functions that were equivalent, but not the same path.
So let me phrase this principle in a more concrete way now that I understand it better. You're essentially saying that you can write extremely different programs that compute a factorial from a given input, natural number input, and one is extremely fast and the other is very slow, but to some extent they are equivalent because they give the same output, just one very quickly and the other extremely inefficiently.
That's a perfect example. Thank
Okay.
you very much. That's a perfect example. Yes.
Good. Thank you.
Okay. So now we also kind of clarify this last sixth law. So there are, after all, 6 laws. We have reflexivity, symmetry, transitivity, congruence, equality, and identity. And we're going to now arrive to our main theorem about equivalence. It turns out that I'm also mindful of the time, so we might not have time to discuss the theorem in full today. But at least let me state it so that those of you who have time to work on it before the next meeting, that you might want to try it out yourself. So let me actually formulate this as a conjecture, but it is actually a theorem. So your question, Fosco, was in the direction of saying, if I know something locally, like I know that that two morphisms are the same, then I should be able to, that should be enough information for me to conclude things in a global scale. And we saw that it's not the case because the local information was too little. We just had single morphism and a single morphism being equivalent. But this idea that you can reduce the concept of equivalence for long paths to something small actually does work. It's just that we need to consider not single compared with single, but two compared with one. So conjecture is that the complete information about equivalence in a graph, and this is not just any equivalence, it's the one that satisfies our axioms. So that satisfies the laws of reflexivity, symmetry, transitivity. Then we had equality law, and we had identity law and congruence law, right? First we had congruence law, and then equality and identity. Transitivity, congruence, equality, and identity. So let me pause here a little bit. So we have this knowledge of when do two paths give the same result. This knowledge of knowing when that happens is the knowledge of the equivalence on our graph, right? And now what we're saying in this conjecture is that this knowledge, this huge knowledge, reduces to knowing the following. So the complete information about equivalence in a graph can be captured by knowing which paths of length 2 are equivalent to which paths of length 1. And let me illustrate this on a picture what I mean. So imagine every time you give me two paths, one of length 2 and the other of length 1. So let these objects be A, B, C. Every time you give me these two paths, one of length 2, two morphisms in the path, the other of length 1. Every time you give me that, I'm able to tell you, I'm going to be able to decide whether they are equivalent or not. So I have the information of whether they are equivalent or not, okay? Then, using only this information, I will know, no matter how long your paths are, I will know whether they're equivalent or not. And now that I said that, I realized that we need one more axiom, and that another axiom is actually similar to the one we had about the identity law. So let me go back to the identity law. Where was it? At the beginning here. So it was saying something about the fact that if that I want to have certain processes included in my graph, right? Namely, the empty paths, they need to be, so the process of doing nothing, they need to be already present in my graph, right? for this conjecture, I might need a similar axiom that tells me that no matter how long a path I have, there should be a single morphism I can select that is equivalent to it. So the identity law actually should apply not just to empty paths, but to arbitrary paths. And let me instead call this the reduction law. So the reduction law of equivalence states that for every two objects, so let me keep that identity law, and then I'm going to call I'm going to rewrite this. But now I see we're closer to the end of our lecture, so maybe we should actually stop here. So this conjecture might or might not be true at this point. And if you want to think about it, you're welcome to. Otherwise, next time we're going to pick up from this conjecture and prove that it's true if it's true. But also we're going to add one more law that I somehow missed, and I'm sorry for that. So in this definition we had here, this identity, if we are defining a category here, then the identity law is not sufficient. We actually want to replace it with the law of reduction, which says that, so I'm not going to formally write it, I'm just going to tell you intuitively. It says that if I have a path of arbitrary length, I should always be able to find a single representation of that process. So a single morphism F. So if I've got G1, let's say G2, G3, and G4, I should always be able to find a single morphism such that this path is equivalent to it. And it's kind of, if I go back, it might seem a bit strange, but if we go back to the train example, it's basically saying that in my graph, I want my morphisms to be not just the train lines between cities, but also any kind of combinations of train lines I can take. I want those to be also seen as one long train line. That's more or less what the axiom will say. Okay. This is officially the end of today's session, but I will still stick around if you have some questions and you want to talk about something. I'm happy to chat more.